Welcome to the sixth lecture of probability and statistics. And I just recall that now we are talking about examples, or we can say basic models of random variables. And last week, we talked about some examples of discrete random variables. I just recall that I showed you the random variable x with alternative or also called Bernoulli distribution, which was the example of a random variable describing a success or failure. So it takes only two values, 1 or 0. Then we consider the random variable with so-called binomial distribution. And the binomial distribution was the distribution used for random numbers describing the number of successes in a given number of trials. The third example, the third model, was the model of Poisson distribution of probability, which was the model for the number of events in a given time period, or it can be used for a given area or on some length. But usually we use it for the number of events in some time interval. And the last example was example of geometrical distribution, which is used for random numbers describing the number of failures before the first success. So it was the topic of the last week, and now I will start with some examples of continuous random variables. The first example is the example of so-called uniform distribution, and I will start with an example as usual. It is the example which I used for a few times before, and it is the example when the number, no, I will write it by words, the time intervals between bus arrivals are 10 minutes. What is the probability that we will wait at least 7 minutes. If we do not know the time schedule. So, I showed you this example when we are talking about geometrical probability. I showed you this example when we were talking about distribution function and density. So now we will call this random number, this random variable, or let's say we will call the distribution of this random variable. So the example was shown when I was talking about density and about distribution function in general. Or I will write x as it is in the slides. And when I talked about the density, I told you that the density is constant because the probability is distributed uniformly. We don't know the time schedule of the bus. So we'll come randomly to the bus stop, and then no times are preferred, times of waiting are preferred. So it means that the taken values, the times we will wait for the bus, are distributed uniformly in the whole interval from 0 to 10. When we consider the time in minutes. The distribution function describing how the probability is accumulated is, of course, 0 in negative numbers, because no probability can be accumulated in negative numbers. All the probability is accumulated till the value 10. So the function is constant from 10 to infinity. And because the probability is uniformly distributed, the distribution function is uniformly increasing from 0 to 10. And now, what is the name and the general example of such a random variable? So when we consider x to be the random number describing the time of waiting for a bus, in minutes, then we say that x has uniform distribution on the time or on the interval from 0 to 10. Yeah? So because the probability is uniformly distributed in the whole interval from 0 to 10, we call this kind of distribution to be uniform. And for such a random variable, the density is, we know that this area must be equal to 1 and the length of the time interval is 10. So it means that this side of the rectangle must be 1 over 10. So the density is 1 over 10 for x from the interval 0 to 10, and it is equal to 0 for x out of this interval. The distribution function is equal to 0 for x less or equal to 0. It is equal to 1 for x greater or equal to 10, and it is equal to 1 over 10 times x for x from 0 to 10. Because it is increasing, it is linear function, increasing linear function, and on the length 1 on the x-axis, the growth is equal to 1 over 10. So this is the idea of this constant. And how the uniform distribution looks like in general. In general, it is a random number which is the density equal to a constant in some time interval from A to B. And because the length of the interval from A to B is B minus A, then the constant is equal to 1 over B minus A, and because it must be 1 over the length of the interval. And the density is equal to 0 outside this interval. The distribution function is of this shape. So in general, we have A and B instead of 0 and 10, A and B instead of 0 and 10. The constant is equal to 1 minus B, 1 over B minus A, and in fact everything is described here, so it's not needed to describe it again. So the distribution function is equal to 0 for x from minus infinity to the lower boundary, because there is no probability which can be cumulated. All the probability is cumulated till the upper boundary, so the distribution function is equal to 1 for x greater or equal to the upper boundary. And between A and B, between the lower and the upper boundary, it is a linear function where 1 over B minus A means the growth and the velocity of growth. And x minus A means that it is linear and it is shifted from 0 to A on the horizontal x. So the shift, so it means that it starts to grow in the point A is given by the term x minus A. So that's the form, explanation of the form of the density. And how is it with expected value and with the variance? So the expected value is, as we expect, in the middle of the interval. The middle of the interval from A to B is A plus B over 2. But of course, it can be also calculated. So I will show you how to calculate the expected value and the variance of uniform distribution. So we know that the expected value of a continuous random variable x is calculated as the integral from -infinity to +infinity x times the density dx. In our case, it is the integral from -infinity to a of x times 0 dx plus the integral from a to b of x times 1 over b minus a dx plus the integral from b to +infinity x times 0 dx. We can see that the first and the third integrals are equal to 0. So we will calculate only the middle integral, and it is 1 over b minus a, which is the constant, times, now we calculate the integral from x, it is x squared over 2 from a to b. So it is 1 over b minus a times b squared minus a squared over 2. And we know that b squared minus a squared is equal to b minus a times b plus a, everything over b minus a times 2. So we can see that it is really equal to a plus b over 2. And what about the variance? So we'll again use the formula saying that the variance can be calculated as the expected value of x squared minus the square of expected value. So we need to calculate the expected value of x squared. Expected value of x squared is equal to the integral, in general, it is the integral from -infinity to +infinity, x squared times the density dx, and similarly as above, we will get the integral from a to b in our case from x squared times 1 minus b minus a dx, which is 1 over b minus a times x powered by 3 over 3 from a to b, and it is b powered by 3 minus a powered by 3 over b minus a times 3, which is b minus a times b squared plus ab plus a squared over b minus a times 3. So it is a square plus ab plus b square over 3. So it means that the variance is equal to a square plus ab plus b square over 3 minus a plus b half square. So it is a square plus ab plus b square over 3 minus a square plus 2ab plus b square over 4, which is the square of this term. And it is equal to 4 a square plus 4 ab plus 4 b square minus 3 a square minus 6 ab minus 3 b square. So 4a square minus 3a square is a square. 4ab minus 6ab is minus 2ab, and 4b square minus 3b square is b square over 12. This is nothing than a minus b square over 12, but we know that p is the upper boundary and a is the lower boundary, so we write it in the form upper boundary minus the lower boundary square over 12 in order to have a positive number, which is more sympathetic, let's say. So this is the way how we got this expected value and variance of a random number, random variable with uniform distribution. Okay. So this was the first example of a continuous random variable. And now we can go to the second example. The second example is again more practical than the first one. The first one was, let's say, just help distribution for some situation we will see on in practice. And now I will show you more practical distribution which can be used separately from other topics. So, when we are waiting for a bus, and we know that the intervals between two bus arrivals are 10 minutes, then we know that the bus will come at latest in 10 minutes. And so we have some upper boundary for this waiting time. But it doesn't hold in practice. And when we are in a shop, or last week we had the example with a bank. Then when we are waiting for a client, there is no upper boundary for this waiting time. And because the client can come in a few seconds, but he or she can come in 2 hours, in 10 hours, in 2 days, we never know. So for the time of waiting for some events, which don't come regularly. We use the model of so-called exponential distribution. The exponential distribution is the distribution with the density of the form such that it is negative. It is equal to 0 in negative numbers because the time of waiting cannot be negative, and then it is decreasing in this way in positive numbers, and it will start in some number lambda. Then the distribution function is of this form. It follows from the density, of course. It is equal to 0 in negative numbers because there is no probability to be cumulated. Then the cumulation starts very fast, and since we have less and less probability in higher values, then the growth is slower and slower and slower. It will be closer and closer to the value 1, but it will never touch it. And this function in a general form is 0 for x less than 0 or less or equal to 0, and for positive x, it is of the form lambda times e powered by minus lambda x. Because the exponential function plays the main role in the density and also in the distribution function, this distribution is called exponential distribution, and it is given by one parameter lambda. It is the random variable with the density given by this description, and the cumulative distribution function given by this picture, where, as I showed you in practice, we can derive the form of the distribution function, in fact, using the integral from minus infinity to x of the density. And when we calculate this integral, we will get that it is equal to 0 for x less or equal to 0, and it is equal to 1 minus e powered by minus lambda x for x greater than 0. So this is the density and cumulative distribution function of the random variable with exponential distribution, and we can calculate the expected value and the variance, as the integral is usually from minus infinity to plus infinity x times the density of x dx, which is, in our case, the integral from minus infinity to 0, or better say, x times 0 dx plus the integral from 0 to infinity x times e powered by minus x times lambda times e powered by minus lambda x dx. And I showed you, as I said, such an example on practice. Lambda was equal to 3. So you can remember that we use the per partes method. And using this per partes method, we got the result 1 over lambda. For calculation of the variance, we again use form expected value of x squared minus the square of expected value. And since the expected value of x squared is equal to, again, write it just briefly as the integral from 0 to plus infinity from x squared times the density we can use 2 times per partes method, and we will get the result 2 over lambda square. So it means that the variance is equal to 2 over lambda square minus 1 over lambda square. So it is 1 over lambda square. Okay? So these are the characteristics of exponential distribution, and now I will show you some example and the method, the approach, how to work with the examples leading to using exponential distribution. So, okay, I will write the example here in order to keep the characteristics for a while there. So, I've mentioned the example from last week, so I will continue in this example. The average number of clients coming to a bank is 3 per hour. What is the probability that the time of maybe the time of waiting sounds better. The time of waiting for the next client is at least half an hour. So last week, the question was, what is the probability that in the following half an hour there will come at least, I don't know, 2 clients or something like that. Now I'm asking, what is the probability that the time of waiting for the next client is at least half an hour? And the solution is the following. We denote x, a random variable describing the time of waiting for the next client. And the time of waiting can be, let's say, in hours. Just note that if you use minutes or seconds or an arbitrary unit, the result will be the same, of course. So I will choose hours, and because it is the time of waiting for some event with no upper boundary of waiting time, which can come in arbitrary time, it is a typical example of the random number with exponential distribution. And now we need to find the parameter lambda. As I delete it right now, we know that the expected value of x is 1 over lambda. And we know that the expected value is theoretical average. So we know that 3 clients per hour is the average number of clients. So it means that the expected value of waiting time is 1 over 3. And because when we have 3 clients per hour, it means that in average we will wait 1/3 of the hour for the next client. And it means that lambda is 1 over the average. So in our case, lambda is 1 over 1/3, is equal to 3. So the parameter of the distribution of waiting time is 3. Maybe it is better to imagine lambda as the intensity. Because 1 over the mean time of waiting is, in fact, the number of events per time unit. And usually it is the information which we have. So maybe better than calculate the expected value in order to take 1 over this expected value and get such a nice number. It is better to look for the intensity. And the intensity is 3 events per unit time, 3 clients per hour. So this is the way how to get the parameter lambda. And when we have this parameter, then it means that we know both the density and the distribution function. And I change it, I start with the positive x here in this case, but it doesn't matter, it is the same, and I start with positive x because it is the more important part, and more interesting, more important part. So now go back to the probability. So we want to calculate the probability that the time of waiting for the next client is at least half an hour. So it means that the time of waiting is at least greater or equal to 0.5. And what is the probability that the time of waiting is greater or equal to 0.5? It is the area below the curve from 0.5 to x. So it is the integral from, in fact, from minus infinity to, from 0.5 to plus infinity of the density three times e powered by minus 3x dx. So it is 3 times e powered by minus 3x over minus 3 from 0.5 to infinity. E powered by minus 3x goes to 0 in infinity. So it is 0 minus minus from here, e powered by minus 3 times 0.5, which is e powered by minus 1.5. Oops. So it is nice that we can imagine this probability as the area below the curve of the density, but the calculation can be in some situations quite difficult because you could see one minus is here, then the second minus is here. Because the lower boundary we have many minuses, we can make some mistakes. So maybe we can skip the calculation of integral and we can use the calculation of the distribution function. So when we calculate the probability that x is greater or equal to 0.5, it is in fact 1 minus the probability of complementary event. And the complementary event is that x, the time of waiting, is less than 0.5. The exponential distribution is the distribution of continuous random variable. So the probability of concrete value is equal, probability of obtain the concrete value is equal to 0. So we can write equality here. And this is nothing than the distribution function in the point 0.5. So it is 1 minus the distribution function in the value 0.5, which is 1 minus 0.5 is positive, so we will use this description. 1 minus e powered by minus 3 times 0.5. 1 minus 1 is 0, minus minus e powered by minus 3 times 0.5 is minus 1.5. And that's the same result again. And so both these approaches are in fact the same because they are based on the same idea. Since the distribution function is the integral of the density, then of course we can calculate this probability using distribution function without calculation of integral because it is calculated here. And so everything is connected. Everything, but it's up to you what is better for you, what do you prefer, what do you like more. And we have one more approach we can use here. So, completely other approach is the following. What does it mean that the time of waiting for the next client is at least half an hour? It means that in the considered half an hour, nobody will come to the bank. And now we don't work with the time of waiting, but we work with the number of clients. So when we denote y, not the time, but the number of clients, in the following half an hour, we have the number of events which are independent to each other. And it is a typical example of the Poisson distribution. It is in fact exactly the random number which we considered last week. So we know that it is the random number, random variable with Poisson distribution where the parameter is equal to 1.5. I just recalled that for the random number with Poisson distribution, the parameter is equal to the expected value. So the expected number, the average number of the clients per half an hour, in half an hour is 1.5. And when we have 3 clients per 1 hour, then in the following half an hour, there will come 1.5 clients in average. And it means that the probability that y is equal to k is 1.5 powered by k over k factorial times e powered by minus 1.5 for all k from 0, 1, 2 to infinity. And as I said, the time or the situation that we will wait at least half an hour for the next client corresponds to the situation that there is no client in the bank in the following half an hour. This probability is equal to 1.5 powered by 0 over 0 factorial. 0 factorial is equal to 1. In numerator, we have 1 as well. So, again, we obtain the probability e powered by minus 1.5. So, even though the question is what is the probability that the time of waiting for an event is at least or at most a given number, we can use the random number describing the number of events. And it holds in general. Now look to the property 2, connection with the Poisson distribution, where we have the property described in words. If the random variable x describes the time of waiting for an event, and this time of waiting has exponential distribution, then the number of such events in time interval of the length capital T has the Poisson distribution with the parameter lambda times t. So, as I said, lambda is considered to be the intensity, the average number of events per unit time, and per time unit. Sorry, and so it means that when we have the time interval of the length t, it must be lambda times t. And when there are 3 clients per hour, and we consider 10 hours, there will come 30 clients in average. When we have 2 hours, there will come 6 clients in average, and so on and so on. And so this holds in general. Exponential distribution and Poisson distribution are connected in this way. The second property is that the exponential distribution has no memory, or it is called that it has no memory. What does it mean? Mathematically, it is described by the first formula. Meaning, in our case, with the bank and clients, the probability that now the client that the time of waiting for the next client is, let's say, 2 hours, conditionally on that we know that we are already waiting for 1 hour, is equal to the probability that we will wait at least 1 hour. And so it means that when we know that we are waiting at least some time y, and we want to calculate the probability that the total time of waiting will be x plus y, it is the same as the probability that we will wait at least x from now. So we can forget how long we are already waiting, and because the situations, the events are independent. So the time of coming of the next client is independent of the previous client. So independently on whether the last client already left, or whether the last client left 2 hours ago, the next client will come in some time. Yeah? So this is the first property, and I will prove it just briefly. Where there's place for it. So I just recall that the probability of the even A conditionally on B is the probability of the intersection over the probability of B. In our case, when we want to calculate the probability that x is greater than x plus y, conditionally on x is greater than y, is equal to the probability that x is greater than x plus y intersected with the even that x is greater than y, but we know that we are working with times. So when here is x, and here is x, or let's say here is y, and here is x plus y, then the intersection of weighting at least y and weighting at least x plus y is weighting at least x plus y over the probability that x is greater than y, which is 1 minus the probability that x is less or equal to x plus y over 1 minus the probability that x is less or equal to y. And it is nothing than the distribution function in x plus y over 1 minus distribution function in y. The distribution function in x plus y is 1 minus e powered by minus lambda times x plus y. The distribution function in y is 1 minus e powered by minus lambda y, which is equal to e powered by minus lambda x minus lambda y over e powered by minus lambda y, which is equal to e powered by minus lambda x. And it is 1 minus e powered by minus lambda x, which is 1 minus the distribution function in x. So it is 1 minus the probability that the time of waiting is less or equal to x, and it is really the probability that x is greater than x. So it is quite easy proof of the first property, saying that there is no memory in this exponential distribution. So it means that the time of waiting for the next event is independent, totally independent of the time of waiting till now. So I will write quite large letters, and I hope it will be enough what I will write here. So the third example, we will go back to the second example of exponential distribution on practice, and we will talk about it in more details. So don't be afraid that you won't understand it. Now I would go to the last distribution I want to show you, and it is so-called normal distribution. The normal distribution is given by two parameters, mu and sigma square, corresponding to the expected value of x and to the variance of x. The density, you cannot see it, so I will write it for you again. The density is quite crazy. It is 1 over 2 pi sigma square times e powered by minus x minus mu square over 2 sigma square. For all x from real numbers. And although the density is quite crazy, or the description for the density is quite crazy, the behavior is very nice. Mu, which is the exponential, which is the expected value, is in the middle of such a curve. And this curve is nothing than Gaussian curve. And so if you ever heard the term Gaussian curve, that's it. And, well, mu is in the middle of the curve, in the place where the peak is the highest. The role of sigma square is the following. It is the variance. So it means that if the variance is larger, then it allows the taken numbers to be more far away from you. So it is more flat in the case that the variance, it means the sigma square, is larger. And if the variance is smaller, the curve must be so that the values are concentrated around you, and with smaller probability, they are far away from you. So this is the role of sigma square, which is the variance of the random number. And how can we work with this random number? It has the distribution function, of course. But the distribution function doesn't have explicit form. And so what does it mean? It means that we don't have an analytic formula for this distribution function. So the distribution function is in the form of this integral, and the integral cannot be calculated normally. So what does it mean? It means that we need some transformation, and it is the transformation which I showed you 2 weeks ago, I think. The transformation there, such that we subtract the expected value and we divide it by the variance of x. Because then we got z with expected value equal to 0. Yeah, you can see it. And variance equal to 1. Okay. And moreover, the normal distribution has the property that using this transformation, we don't change the type of the distribution. So the distribution will stay normal. So it means that such a random variable has normal distribution with expected value equal to 0 and the variance equal to 1. Then the density is of much better form. Sigma square is equal to 1. Mu is equal to 0. So it is much simpler than before. And it doesn't mean that now we can calculate the integral. But we can find the values of the distribution function in a special table called statistical table, or the table of distribution function of standard normal distribution. And so this distribution is called normalized or standard normal distribution. And the values of its distribution function which is in this case denoted as phi, Greek letter. So it is still the distribution function, but it has a special notation because it is really a special distribution which has many usage later in so-called central limit theorem, in statistics and so on. Yes, so because it is a really special distribution, its distribution function has special notation, and the values can be found in so-called statistical tables. I will show you these tables in practice. It can be they can be found also on my web page, everywhere in internet. So we will talk about it about this on practice. Now I will show you one example of calculation with this normal distribution. This distribution is used in many fields, because in fact it models everything what is or whose behavior is such that the values are most often around some given value, around the average value, and with lower probability they are far away from this value. So it can be height, weight of people, of animals, of trees, or of plants, and also in finance, it is in fact the difference between some trend, between some let's say constant price, or between some evolution of the price and the real price. What do I mean? Let's consider a course euro to Czech crowns, which is in fact random variable, because every day we have another price of euro in crowns. So it is random variable x, and let's suppose that the mean value is, let's say, 25 in order, it is easy, and 0.49 is the variance. Yeah, so I'm talking about daily prices, about the price which you read in a newspaper every morning. And we observe in the last few days that the mean value is 25 and the variance is equal to 0.49. What is the probability that next Monday the price of euro in Czech crowns will be at least 24 times 30. Yeah? So the price of, let's say, 1 euro will be 24.30 Czech crowns. So we want to calculate the probability that x is at least 24.3. And we cannot work with x, but we can work with transformed x, with the x from which we subtract the expected value and we divide it by the square root of the variance. And now we have the inequality in the brackets. So what we did on the left side, it must be done on the right side as well. We know that on the left side we got a new random variable z with standard normal distribution. It means with normal distribution with 0 mean value and the variance equal to 1. So it is the probability that z is, and now we can calculate this value. So it is minus 0.7 over 0.7. So it is in fact minus 1. And we know that we can find the distribution function of z in statistical table. Distribution function is the probability that z is less or equal to something. We have z greater than something in the brackets, so we must calculate this probability as 1 minus the probability of complementary event, that z is less or equal to minus 1, and it is 1 minus phi in minus 1. And this number can be found in the statistical table. One small remark, the statistical tables are usually organized so that you have the values of positive variables only. Why? Because the density of standard normal distribution is symmetric around 0, and then the probability And the distribution function of minus a is equal to the probability that z is greater than a, yeah? Because the area of this tail is the same as the area of the left tail. Yeah? So it is, in fact, the probability that z is greater than a. But it is 1 minus the probability that z is less or equal to a, which is 1 minus phi in a. And so there exists a symmetric relation. So it means that if we have the table for positive variables only, we can write this distribution function as 1 minus phi in 1. And it is phi in 1. And in the table, which I will show you on the exercise, but for now, believe me, that you can find the value 0.8413. And so this is the way how to calculate with random variable with normal distribution. First, we need to transform this variable to the random variable with standard normal distribution. What is done on the left side, it must be done on the right side as well. And then we have the probability that z is greater than something or less or equal to something. We work with z, whose distribution function is known. The values of the distribution function can be found in the statistical tables. And so when we have the probability that z is greater than something or less or equal to something, it is done, because everything else can be read in the tables. Okay, so that's all for today from the lecture. I hope it was seen at least through these themes, and I'm sorry for these complications. I'll try to notice what happened, and I believe that there will be at least the record of this lecture. So if you miss something, you can find it on the record of this YouTube. Okay, are there any questions? Comments? Okay, so if not, I thank you for your attention and thank you for your cooperation using this recording and solving these technical things. And see you in approximately half an hour at the exercise.